Life cycle costing analysis is a big topic in certain sectors of design, like civil, transportation, construction, and capital equipment. We can use it for our smaller product designs too, to compare our design choices where it makes sense. We talk more about life cycle cost analysis after this brief introduction. Hello and welcome to Quality During Design, the place to use quality thinking to create products others love for less. My name is Dianna. I'm a senior level quality professional and engineer with over 20 years of experience in manufacturing and design. Listen in and then join the conversation at qualityduringdesign.com. It costs our customers to own our designed products. It costs them initially to purchase it, but it also costs them to use it, maintain it, repair it, and eventually dispose of it. And it costs our company in ways too, like processing, training requirements for customers, and warranty repair costs. A life cycle cost analysis can help our team choose between design alternatives, like alternate design options, features, manufacturing methods, or suppliers. A reason to perform this type of analysis that I consider most as a quality and reliability engineer is to lower the ownership cost of our products without sacrificing the product's functionality, quality, and safety. If our system is repairable, it can also help us determine maintenance schedules and spare parts needed, or even help us determine if the warranty period is set appropriately. And it's best done at the early concept and design process phases of the design cycle. This is because the decisions made at these early phases affects many more decisions as we develop our designs. A life cycle cost includes the cost to purchase, operate, and maintain the product during its useful lifetime. We can use life cycle cost analysis to help determine alternatives of a design, to estimate overall cost of a project's alternatives. It's not used for project budget allocations. A simplified way to describe the procedure is we figure out the economic impact of the alternatives we're evaluating. Then we translate those alternatives into monetary terms. Our decisions to choose one design option alternative over another may raise initial cost of purchased components, but then it will reduce the overall operations, failure, and support costs over the lifetime of the product. Do our options balance out? A broad definition of a life cycle cost equation is the life cycle cost is the sum of the acquisition costs, operations costs, failure cost, support costs, and disposal cost. There are a lot of costs associated with this life cycle cost equation. When considering it, we usually only consider those costs that have a big impact on the life cycle cost. But let's talk a little about each one of these costs to get a better understanding of their scope. Acquisition costs are the costs to design and produce our product, including things like management and distribution. It costs the company to acquire a product to sell, and this cost is representative of that. This acquisition cost gets added to our life cycle cost. Operation costs include things like facilities, operators, consumable energy, and fuels. Failure costs are those involved with warranty, repair, or replacement. Support costs are associated with product support, like customer help centers and training the customer to use the product, or preventive routine maintenance. And we may also want to consider the cost of disposing our product at the end of its life cycle. These costs can be added to the life cycle cost also. A cost that could get subtracted from our life cycle cost is any reimbursement at the end of life of the product, like its salvage cost. It's good to think ahead with all of these costs. Say we are comparing two components from a supplier. One is expensive to buy and the other is cheaper. The expensive component has a high acquisition cost and has the best performance and quality, so its failure cost is low. but its frequent maintenance requirements add to the support costs, and it's difficult to recycle and dispose, adding to those costs too. The cheaper component does not perform as well, but it requires less costs in the way of maintenance and is easy to recycle. If the failure cost of the cheaper component is not high, it may have the overall lowest life cycle cost. Here's the thing. When we're designing, we're not just looking at costs. This is just one aspect of design engineering that may affect our decision. The reliability of a product and its safety may take a higher priority. Comparing components or design options using a life cycle cost analysis all sounds good in theory, but how do we do this? An internet search on life cycle cost analysis gives us lots of accounting websites, and an NIST government-published document about life cycle cost analysis that is about 250 pages long. This is the type of topic that we can easily get paralyzed with, not knowing how to even move forward because there is so much information. Plus, the costs that we're considering are not exact. We need to make assumptions about it. The first thing to assess is this. What are the costs that are sensitive to the design reliability of our product? If we're looking at new capital equipment that's installed for a long period of time, there are a lot of costs we can consider. The recurring costs could be its cost to operate it, the inventory and support costs, the costs of operators, and its maintenance cost. Non-recurring costs could include its costs for procurement, installation, qualification, training, and its reliability and maintainability costs. However, when considering what costs are sensitive to the design reliability, if we're looking at a smaller, simpler design, chances are we will not have so many costs to consider. We are allowed to assume that the acquisition cost and failure cost are the two costs that are the most sensitive to our design reliability. If that's the case, then we can focus on those two costs. The acquisition cost may be easy to figure out if it's a purchase component. The acquisition cost is basically the purchase cost of the item. Otherwise, we can talk to our accounting or management friends to help figure out a more exact acquisition cost for something we're designing in-house. The failure cost will also require some assumptions and calculations. Failure costs could be the product of the failure rate, the expected life of the product, and the cost to repair and have spares on hand. Now, who would help us with the failure rate and the expected life of the product? Our reliability engineering friends, of course. I'll post the equation to this specific life cycle cost model on the podcast blog. We can't totally ignore economic aspects, like future costs. There are a lot of ways we can convert today's money value into a future day's money value. Depending on our design, we may need to consider things like interest and depreciation. If we feel that could affect our life cycle costing analysis, we could consult with an accountant. Our company may have standard ways of calculating these things. If you are unsure about how to use this for your design, or you feel your design is more complicated, then I recommend the book Life Cycle Costing for Engineers by Professor B.S. Dillon. He authored it as a general book on life cycle costing, and it includes a lot of other references. We can use the book as a jumping-off point, find what might be applicable to our case, and then look more into it with the references provided. The key takeaway? When choosing a component or design option based on cost, let's widen our view from procurement cost to include costs of our choices over the life of the product. The cost of a design goes well beyond just purchasing or making it. We can use life cycle cost analysis to compare design options as just one example of its use. We can make assumptions for our life cycle cost analysis based on what aspects of costs are applicable to our design. We just need to document or acknowledge any assumptions that we make. We can speak with our accounting friends to ask about the economic standards our company might use when making these decisions, like interest, depreciation, and standard costs of R&D development. We can also talk with our reliability engineering friends about failure rates and the expected life of the product. Life cycle costing doesn't have to be too complicated, and it is a way we may be able to evaluate our choices. Please visit this podcast blog and others at qualityduringdesign.com. Subscribe to the weekly newsletter to keep in touch. If you like this podcast or have a suggestion for an upcoming episode, let me know. You can find me at qualityduringdesign.com, on LinkedIn, or you could leave me a voicemail at 484-341-0238. This has been a production of DIANNA Enterprises. Thanks for listening.